Okay, thank you, Yuval. And so, of course, I would like to thank the organizers for making me a part of this event. So I'll talk about combinatorics of Cuntz algebras, and this is my plan. So I will start with an introduction to Cuntz algebras for combinatorialists. Then I'll talk about stable permutations. And then I'll talk about combinatorics of stable permutations. And then I'll mention some algebraic applications of these combinatorial results. And then if I have time, I'll talk about some open problems. So as the title suggests, this is an informal introduction to Cuntz algebras, definitely not the formal definitions, but so this is how I first understood Cuntz algebras when my mathematical physicist co-author Roberto Conti first explained them to me. So that's what I want to do. So I want to share with you this understanding that I gained of Cuntz algebras, which is very operational. So as you'll see, I will be informal, but I will give you a feel for what it's like in practice to work and compute in this algebra. So just to avoid any misunderstanding, for a set A, S of A is the set of all bijections from A to A, so the symmetric group on A. And if I have two such bijections by F times G, I mean F composed with G. So first I apply G, and then I apply F. And I'll denote by 1 index A, or simply 1, the identity permutation on A. So I will write permutations in this joint cycle form, and I will omit the 1 cycles. So as usual, by n in the square bracket, I mean the integers from 1 up to n. So for example, if I take as A 7 squared, Cartesian product of the numbers from 1 to 7 with themselves, and I take as F this permutation, so product of these 2 cycle and this 3 cycle, what I mean is that 1, 2 goes to 2, 1, 2, 1 goes to 1, 2, 4, 5 goes to 5, 7, 5, 7 goes to 2, 3, and 2, 3 goes back to 4, 5. I will also represent F by its functional digraph. So by the way, P for me is the positive integers. So if I write this diagram, then I mean that I have this permutation of 7 squared, and it sends 1, 3 to 1, 4, 1, 4 back to 1, 3. It sends 3, 4 to 5, 6. It sends 5, 6 to 6, 3, and 6, 3 back to 4, 3. 3, 4, excuse me. Okay, so let me start with this introduction to Cuntz algebras for combinatorics. So you take a positive integer greater than or equal to 2, and I'll consider a set S, and I'll call its elements S1, Sn. And I'll consider another set, which I call S star, and its elements I'll write S1 star, Sn star. So if I have a composition alpha in n to the k, so these are k integers, each one from 1 up to n, then I'll use this shorthand notation. I'll denote by S alpha the word S alpha 1, S alpha k. You can think of it as a product if you want. I would say a word. And I'll denote by S alpha star, S alpha k star, S alpha 1 star. So somehow the star reverses the order of the factors. Okay, so and now I assume that these symbols S1, Sn, S1 star, Sn star satisfy these relations. So the sum for I from 1 up to n of Si, Si star is 1, number 1. And the product of Sj star Si is delta ij1 for all ij. So if j is different from I, this is 0. If I is equal to j, this is 1. So I'll leave this for a couple of seconds so that you can absorb them a little bit. So I have this sum equal to 1, and then this thing here.
And this is only from this side. The SI, SJ star, you don't impose anything, right?
Exactly.
Okay.
SI, SJ star, I don't impose anything, exactly. So now I'm going to consider this set. I'll call ON tilde, and this will be all finite linear combinations of words in this alphabet, coefficients in C, and subject to these relations. So now, of course, you see immediately that if I have any word in S union S star, because of this, whenever I have an S star followed by an S, this simplifies to a number, either 1 or 0. So in practice, I can assume that all my words are a bunch of S's followed by a bunch of S stars. So ON tilde will have this form. So it will be a finite sum over some set of compositions, some complex number, C alpha beta, S alpha, S beta star. So I'll call this the combinatorial core of the Cuntz algebra. This is my terminology. And the Cuntz algebra itself is the closure with respect to a norm that I will not define of these linear combinations. So in practice, the Cuntz algebra is the set of all Cauchy sequences in these elements. So this is what I just said. ON is the set of all Cauchy sequences. Well, of course, I've defined it, as you saw, in a very informal way. And so it's natural to ask, whether these axioms are contradictory. Do they really exist? Yes, they do. In reality, S1, Sn are isometries on an infinite dimensional Hilbert space. S1 star, Sn star are their adjoints. 1 is the identity operator, and the norm is the one that the operators inherit from the Hilbert space. So Cuntz algebras are a notable family of sister algebras. They are widely studied. About 10 days ago, I checked on MassSciNet, and there were 435 papers containing the word Cuntz in the title, and 380 containing the word Kastner-Lustig in the title. So they are widely studied. They have applications to quantum field theory and to dynamical systems. And more generally, sister algebras are fundamental objects in one of the mathematical descriptions of quantum physics, in which to any region of space-time is associated a sister algebra. So just a few very basic references. So this is the paper where the algebras were first defined. This is the paper where the K-theory of these algebras was first studied. And this is a paper that focuses on the role of this kind of algebras in particle physics. So as in any sister algebra, you have a unitary group. So this is all the elements such that U star equals U star U equals 1. And you have also N of ON. So this is the set of all linear functions from ON to ON that send 1 to 1 and that send the star to the star. So unital star endomorphisms. So particularly important unitary is this F. It's a sum I from 1 to N, sum J from 1 to N, SI, SJ, SI star, SJ star. And I won't really use it in the talk, at least not in a way that you would see. But I want to check with you that indeed this is a unitary, so that you see at least one computation in this Cuntz algebra and you get a feel for it. So let's do it. Fs star, well, F, here it is. some ij, si, sj, si star, sj star, f star, here it is. So star, I didn't say it, it's an involution, so star star is the identity. If you apply star to this and it's linear, you get some KL and you reverse the orders, but it's just the same, nothing changes. I have SK, SL, SK star, SL star. So of course you bring the summation outside and you have this big monomial or word if you want. Si, Sj, Si star, Sj star, Sk, Sl, Sk star, Ss star. But well, now you see, of course, that here I have an S star followed by an S. So this is 0 except when k equals j, so summation over k goes away. When k equals j, this is 1, okay, so it disappears. Now I have Si star SL. So again, this is 0 unless L equals to I, so the summation over L goes away. And when L equals I, this is 1. So in the end, we are left with summation over I and j, Si, Sj, this has all disappeared, k has to equal j, Sj star, L has to equal I, Si star. So now I can rewrite this in this way. I keep the sum over I in front, Si, and then sum over j, Sj, Sj star, Si star. This is 1 because of our relations, and once this goes away, again, this is 1. So this is indeed a unitary. So there is a bijection between the unitaries and the endomorphisms of this algebra. It's to any unitary U, the associated endomorphism is usually denoted by lambda sub U. And this is defined in a very simple way. So I only need to define it on the generators. And lambda U of Si on the generator Si is simply left multiplication by U for all i's. And this is called the Cuntz-Takesaki correspondence. So now inside the unitaries, there is this special subset denoted by P and T. And here it is. So what's special about this compared to the combinatorial core of the Cuntz algebra? Well, two things are special. So here the coefficients are not complex numbers, but they're either 0 or 1. And the other thing is that alpha and beta have the same length. So alpha and beta both are compositions with the same number of parts. Okay. And so there is a bijection between this subset of the unitaries and the symmetric group on n to the t. So t tuples of integers, each one from 1 up to n, and it's given in the following way. If you have a sigma permutation of n to the t, you associate this unitary. So it's a sum over all sequences in n to the t.
What is T here? T is the size of the big set S. What is T?
No. N is the size of S. T is, so I've just introduced it really. So you see in this Cuntz algebra, you have these words, and in a sense, they have a degree, right? Number of parts of alpha is the number of S's, number of parts of beta is the number of S stars.
Right.
And what's special there is that these are kind of homogeneous. So the number of S's and the number of S stars are the same, and I denote the number by T.
Oh, so T is the one when the length is T. It's not the unit. Okay.
Exactly. Okay. It's the one where the length is T. So
okay,
you have... No. So you fix it, and for any T, you have the one such subset. So what's the unitary corresponding to sigma? You just take S indexed by sigma of alpha, okay, and S alpha star. So I'll illustrate this with an example. Suppose n is 4 and t is 2, and I have this 3 cycle in 4 square. Okay, so what's the corresponding unitary? Well, sigma sends 22224, so I have S24, S22 star. It sends 24242, so I have S42, S24 star, and it sends 42 back to 22, so I have S22, S42 stars. And then I have all the fixed points, and in all the other elements ij goes to ij, so I have Sij, Sij star. So this would be the unitary corresponding to this permutation. So the following problem is the main motivation for the applications of combinatorics to the theory of Cuntz algebras. So for which U in P and T, is it true that the corresponding endomorphism is actually an automorphism? And more generally, one may ask for which unitaries is it true that lambda U is an automorphism? So this problem has a combinatorial solution. This problem is open. Okay, so now those of us that are of a certain age, we well know that when this paper was written by Cuntz, it was written, as you can see, in 1980. Combinatorics, aside from a few enlightened places around the world, such as MIT, was considered an area of mathematics with essentially no connections to anything else inside or outside of mathematics. But here is this mathematician coming from a completely different area, coming from operator algebras. And at the end of this short paper, he says, the classification of all automorphisms, blah, 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 is a combinatorial problem and should be possible. So I really give credit to the guy who, as I said, coming from a completely different area of mathematics, really recognized this as a combinatorial problem. Okay, so here I am now to then stable permutations. So we have two sets now, A and B. I have a permutation F of S of A, G of S of B, and I'll define the tensor product of F and G to be the permutation, which I'll denote F tensor G. It's a permutation of the Cartesian product of A and B. And it's defined simply in this way. F tensor G on a pair AB is just F of A, G of B. So F acts on the first coordinate, G acts on the second for all ABs. Okay, so now we fix an N, a T, positive integer, and a K, non-negative, and the permutation U of N to the T. So by the way, N for me is the non-negative integers. So I'll define a new permutation, psi sub K of U. This is permutation of N to the T plus K. And it's defined in the following way. So it's a product of permutations. The first permutation is 1 tensor 1 tensor 1 tensor U inverse. So U acts on T tuples on numbers. 1 is the identity of the symmetric group. It acts only on one number. So 1 tensor 1 tensor 1 K times acts on K tuples. So the whole thing really acts on K plus T tuples of numbers from 1 to N. So this is my first factor. Then I'm going to move U inverse to the left by 1. So I have 1 tensor 1 tensor 1 K minus 1 times, then U inverse, then 1. And I continue doing this. U inverse goes to the left until eventually it goes to the first position, and you have 1 tensor 1 tensor 1 K times. Now U inverse goes back to the right, but becomes U. So you have U tensor, 1 tensor U tensor 1 tensor 1 tensor 1 K minus 1 times, etc., all the way to 1 tensor 1 tensor 1 k times tensor u. And the product of these permutations is what I call psi k of u.
There is no factor u1111.
No, exactly.
So
Exactly. If there was, everything would collapse and this would become the identity.
yeah.
Or if there was in here, then it would collapse.
Thank you.
Yeah. Okay, so I'll illustrate this with an example. So suppose n is 7 and t is 2, and I take this permutation of 7 squared, a 2 cycle, and a 3 cycle. I'm going to compute psi sub 4 of u. So u acts on pairs of numbers, and I have a 4 here. So psi 4 of u acts on 6 tuples of numbers, each one from 1 to 7. So I'm going to compute psi 4 of u on this particular 6 tuples, 1, 5, 5, 2, 4, 3. So I remind you that multiplication for me is composition of functions. So the first one that I apply is this one. Okay. So here we are. We have 1, 5, 5, 2, 4, 3, and I have to apply u to 4, 3. U to 4, 3 is 3, 4. So 4, 3 becomes 3, 4. And u moves one step to the left. So now you have to apply u to 2, 3. U of 2, 3 is 1, 2. So 2, 3 becomes 1, 2. And u moves one step to the left. So now you apply u to 5, 1. 5, 1 is a fixed point. So 5, 1 remains 5, 1. U moves to the left. You have to apply u to 5, 5. 5, 5. U sends 5, 5 to 2, 3. So 5, 5 becomes 2, 3. And u moves to the left, but now becomes u inverse. So you have to apply u inverse to 1, 2. U inverse to 1, 2 is 2, 3. So this becomes 2, 3. U inverse moves to the right. So now you have to apply u inverse to 3, 3. 3, 3 is a fixed point. So 3, 3 remains. U inverse moves to the right by 1. Now you apply u inverse to 3, 1. That's also a fixed point. So 3, 1 remains. U inverse moves one step to the right. So now you have to apply u inverse to 1, 2. U inverse to 1, 2 is 2, 3. Is 2, 3. So 1, 2 becomes 2, 3. And u inverse moves to the right. And finally, we have to apply u inverse to 3, 4. U inverse to 3, 4 is 4, 3. So this becomes 4, 3. And this is it. So size of 4 of 1, 5, 5, 2, 4, 3 is 2, 3, 2, 4, 3. So let's then take our permutation as above, u a permutation of n to the t, and we say that u is stable if there is a positive integer k sub 0, so that psi sub k of u is psi sub k0 minus 1, tensor 1, tensor 1, tensor 1, an appropriate number of times for all k is greater or equal to k0. So psi k0 of u is supposed to be psi k0 minus 1 tensor 1, psi k0 plus 1 supposed to be psi k0 minus 1 tensor 1, etc. And in this case, the least such k0 we call the rank of u. So in n square, so here t is 2, there is a nice way to see, if a very quick way to see if U is stable of rank 1, it simply means that it satisfies this equation. So that U tensor 1 and 1 tensor U commute. So this equation is a relative of the Yang-Baxter equation, which would be 1 tensor U, U tensor 1, 1 tensor U equals U tensor 1, 1 tensor U, U tensor 1. But there are no connections between the two. In fact, one can show easily that the only permutation that satisfies them both is the identity, so they are disjoint. But it's a sibling of the Yang-Baxter equation. So why stable permutations? Well, in 2011, Conti and Zimanski, in transaction of the AMS, proved this theorem that you take a permutation of n to the t, then U is stable if and only if lambda U is an automorphism. So the problem now is to understand which permutations are stable. So combinatorics of stable permutations. So most of the results I'm going to talk about today are for n square. We have results also for more general t, but there is no question that n square is hard enough. Excuse me. So we started with n square. And not only that, but of course, as we all know, if you're going to try to do something for permutations, you typically will start with the simplest possible permutations, namely transpositions, and more generally cycles. So I will speak a lot about cycles, not exclusively, and more or less I'll tell you the state of the art about cycles, and then I'll mention some other things as well. So you take your U, permutation of n square, and I define two subsets, R of U and C of U, subsets of the integers from 1 up to n. So R of U is all the numbers I from 1 up to n, so that there is a j, so that U of j is not ij. So what we are saying is that I is in R of U if in row I there is at least one element that's not fixed by U. So I is in here if there is at least one element in row I that's moved by U. So in other words, if I is not in R of U, then it means that all elements in row I are fixed points of U. And similarly, C of U, so I is in C of U, if there is at least some element in column I that's moved by U. So here's an example. Take n equals 6, take U this product of a 3 cycle and a 2 cycle. So what are the rows that contain at least an element that's not fixed by U? Well, 1, 2, 4, 5. So here's R of U. What are the columns that contain at least an element that's moved by U? Well, 2, 3, 4, 2, 3, 4. So this result we proved with Roberto Conti first for transpositions, and then we were able to extend it with Gleb-Janashev to any cycle. So again, here it's n square. It's a cycle. And then the following are equivalent. U is stable of rank 1, and R of U intersection C of U is empty. So it's very explicit. You couldn't ask for anything better. And this also enables you to count these permutations. You can do it, and you get this formula. Here, so you fix an R, and you're counting the stable R cycles of rank 1 in n square. If you want all of them, you just sum over R. And here, Ci of R is the compositions of R into I parts. So you see that this number is a polynomial in R. In fact, it's a polynomial in N, polynomial in N of degree 2R, and leading term 1 over R. So this has this surprising consequence. Take an R greater or equal to 2, then as N goes to infinity, almost all R cycles in Sn square are stable of rank 1. So if you fix R equals 17 and pick a 17 cycle at random in Sn square, as N goes to infinity, the probability that this is rank 1 is 1, is almost sure that it is stable of rank 1. And this is surprising for a reason that you will see shortly. So of course, now it's natural to wonder, are there cycles of rank bigger than 1? Yes, there are. You don't have to solve, not for transpositions. Transpositions are all of rank 1. If they are stable, they are of rank 1. But as soon as you look at 3 cycles, maybe this is the simplest example in N equals 4, take this 3 cycle, 1, 2, 3, 2, 1, 3. So it's this right triangle. Then this is a stable of rank 2. I could put here instead of 1, 2, and 3, I, j, and k, and this would still be true. It's something that we proved. So these 2 elements in the same row, these 2 elements in the same column, and this further equality. So not all right triangles work, but with these equalities, they are stable of rank 2. So take an R cycle in N square, and I assume that it is a rooted R cycle, so by which I mean that I have chosen a first element, A1, B1. So of course I have R possible choices, as we will see. It doesn't matter which one I choose, but I need to choose one. So then I'll associate to this cycle a direct graph, which I'll denote by S plus of U. Its vertices are the numbers from 1 to R, and the edges, the directed edges, are defined as follows. So you put a directed edge from I to J if either AI equals Bj or AI plus 1 equals Bj. And the indices are modulo R. So let's see an example. I take the same 3 cycle I had above, 1, 2, 3, 2, 1, 3. What are so the vertices are the integers from 1 up to 3. It's a 3 cycle. And so what are the edges, directed edges coming out of 1? Well, 1j is an edge if and only if either A1 is Bj, well, this is A1, it's not equal to any Bj, or A2 is Bj. Well, A2 is 3, and it's equal to B3, so you have a directed edge from 1 to 3. What directed edges come out of vertex 2? Well, 2j is a directed edge if either A2 equals Bj, yes, A2 equals B3, and I have a directed edge from 2 to 3, or A3 equals Bj. I don't really need to do this, but anyway, A3, it's 1, it's not equal to any Bj. Are there any directed edges coming out of vertex 3? Well, you have a directed edge from 3 to j if and only if either A3 is Bj, A3 is 1, it's not equal to any Bj, or A4 is Bj, but A4 is A1, and it's also not equal to any Bj, so you have no arrows coming out of vertex 3. So this is your directed graph. So then the result is the following. We are in N square. You have an R cycle. Then if S plus of U is acyclic, then U is stable. And if R is less than or equal to 4, then the converse is also true. So it's acyclic if and only if it's stable.
And if R is bigger than 4?
Pardon me? Yeah, exactly.
Do you have counter example or?
Yeah. I'm about to say it. So if R is greater than or equal to 5, no, this is not true. So this implication is not true for R equals 5. And so what can you do? So we can define another gadget related to the other one. So here's again our R cycle, and it's a rooted cycle. I've chosen a first element. So by the way, here you see that if we choose another first element, all that changes is that the labels of the vertices change cyclically, so clearly it's a cyclic. For one, it's a cyclic for all of them. And so here, similar situation, you fix your first element, and I define S of u as a subset of R square, integers from 1 to R, Cartesian product. And it's defined in this way. You put a pair ij in your subset if ai equals bj. So this is really very simple. You just record when is an ai equals to a bj. So example, n equals 6, you take this 5 cycle. Well, A1 is equal to B3 and B4. Here they are. A2 is equal to B3 and B4. Here they are. A3 is not equal to any Bj, nothing there. A4 is equal to B1. Here we go. So the result is the following. Take your cycle in n square, a 5 cycle. Then the following are equivalent. One is that U is stable. And the other one is that either S plus of U is acyclic or S of U has this form for some J, modulo 5, the numbers, which means that S of U is one of these configurations. Now, notice that these configurations are really just one because this is obtained from that one by going down one to the right and one down, and so on, in a torus, of course, cyclically. So in practice, we are saying that S of U is equal to this configuration up to a cyclic shift. So this is pretty much we do have results here and there, but this is pretty much the state of the art for what concerns cycles in n square. Now, of course, cycles are a very nice class of permutations, but another class that we all know usually behaves much better than the general permutation is involutions. And in our first paper with Roberto in 2021, we had a conjecture about this case. So product of two transpositions, the two transpositions are horizontal and they're general. I don't care about the columns, but they have to be different rows, not in the same row. So two horizontal transpositions in different rows, and we conjecture that it's stable of rank 1 if and only if this happens, and this Chinese mathematician recently proved this. So it's stable of rank 1 if and only if R of U intersection C of U is empty, or R of U equals C of U. We then generalize this in another direction, but I'm not going to talk about that. Rather, I would like to simply point out that this kind of result is from what we have seen kind of typical. So if you take a permutation, if somehow the parts of the permutation, the rows and the don't interact, the permutation will be stable. If they do interact, they have to be interacting in a very, very specific way for the permutation to be stable. So here's one more result that I want to mention. So fix some integers t, a1 up to ak greater or equal to 2. Then the number of stable permutations, and here we have a general t, with cycle type, this cycle type is a polynomial in n. So you fix the cycle type and in general t, and it's a polynomial. So we are talking about numbers. So of course, one wonders, what are these numbers? So given an n and the t greater or equal to 2, if t is 1, all permutations are stable. I didn't mention that. And so let this number be what we want, the number of permutations in n to the t that are stable. So very few of these numbers are known. I think also some with 3 are known, maybe 3. So I'll focus here only in t equals 2. Only 4 of them are known. Of course, you understand this is S16. 16 factorial is a big number. And so there is 1 for 576, 10,020. And these numbers, as well as our own experience in working with these permutations, suggest that these permutations are extremely rare. And this we could prove. So if you fix a t greater or equal to 2, then the ratio of stable permutations over all of them goes to 0 as n goes to infinity. And similarly, if you fix an n greater or equal to 2, then this same ratio goes to 0 as t goes to infinity. So if you take a permutation at random, probability that is stable is 0, as either n or t go to infinity. Okay, so here are some references. All the results I've mentioned, plus many more, are contained in these papers. And so they're all here. So I want to conclude with some algebraic applications. So of course, stable permutations are not a group. So excuse me. And here I have exactly that observation. It's easy to see that if U of V are stable, the product is not going to be stable in general. And also, the product of the corresponding endomorphism is not lambda UV. But of course, the automorphisms do form a group. And there is interest in finding subgroups of this automorphism group. So we thought that we could apply all that we had learned on the combinatorics of stable permutations to finding some of these subgroups, and this indeed we could do. So, so as I said, it's not always true that if U and V are stable, then the product is stable, but it is true in this case. So if you know that V tensor 1 commutes with 1 tensor U, then yes, it's true that U is stable implies their product is stable. And you also have a bound on the rank, that the rank of U, V is at most the rank of U plus the rank of V. So this condition proved to be so useful for us that we gave it a name. And so we say that two permutations are compatible. U is compatible with V if one tensor U commutes with V tensor 1. And more than that, we say that U and V are B-compatible if U is compatible with V and V is compatible with U. And by what I just said, you see that if you have here n squared, you have n permutations which are mutually B-compatible. This implies in particular that each one is B-compatible with itself, which is like saying that it is stable of rank 1. Then the subgroups generated by them in Sn squared is isomorphic to the subgroup generated by the corresponding automorphisms in auto n. And so we thought that maybe we could, produce B-compatible subgroups to produce subgroups of auto n, and in fact, even more than that, even go to the quotient to outer automorphisms. And this proved to be successful. So we found many B-compatible subgroups that gave us these other subgroups. Sometimes it was a slight variation, but often this was a good object to look for. And so just one notation: if V is a subgroup of the group of permutations of n squared, and all the elements are stable, then I just denote by lambda V the corresponding set of automorphisms. So I think maybe I said it already, we call a B-compatible subgroup a subgroup in which all the elements are mutually B-compatible. So I'll show you one example of such a subgroup. We have several, but I'll just mention one. And so you take a subset of the integers from 1 up to n and define a subgroup by these conditions. So don't look at them, I'll just show you an example. So suppose n is 18 and p is 4, 7, 8, 11. So here's an 18 by 18 grid. So permutation is part of this subgroup if and only if what? Well, on columns indexed by 4, 7, 8, and 11, the permutation does nothing at all. So there, the permutation does not move these columns. They're all fixed points. The green cells in each row, so this one here, etc., are permuted arbitrarily. So the green cells in this row are permuted arbitrarily, in this one, etc. Of course, the pink cells are fixed. And the white cells in each row are permuted all in the same way. So if in the last row they are permuted in a certain way, all the others are permuted in the same way. So this is our subgroup. And this is the result that we obtained. Then this is a B-compatible subgroup. It's easy to see. It's isomorphic to Sn minus cardinality of P to the cardinality of P plus 1. You have something similar for columns. And indeed, if cardinality of P is 1, so you get an isomorphic subgroup of out of n in general. And if P is 1, you get a corresponding subgroup in the outer automorphisms also. So even after taking the quotient by inner automorphisms, it remains isomorphic to this. So as I said, we have 7 or 8 results of this sort. In fact, in a paper that's still to be submitted, although it'll be submitted soon. And I see here that I some reason I forgot to say that this is also by myself, Conti, and Nenashev. So rather, I want to give an idea of what kind of reasonings, very briefly, what kind of techniques are used to come up with these subgroups. Some we could guess, or I should say Roberto Conti, who has an intuition for Cuntz algebras, could guess, but others we constructed with this kind of techniques. So very briefly, I'll go through this. So you take a B-compatible subgroup of Sn squared, and we attach to this subgroup 2 graphs in this way. So GR and GC. The vertices are the integers from 1 up to n. And what are the edges? So it's an undirected graph. You put an edge between A and B, if and only if there is an X and the Y in n and an element in the group. So this is true. So in practice, what does it mean? You put an edge between A and B if there is some element in your group that can move some element in row A to some element in row B. Okay. So you put an edge between A and B if there is some element of your group that can move some element in row A to some element in row B, and the same for GC. You put an edge if there is some element in the group that can move some element in column A to some element in column B. And this graph has some interesting properties. So very, very briefly, so take, for example, AB in the same connected component of GR, a number C and an element of the group. Well, if you take two elements in the same row and in these two columns connected in GR, then after you apply any element of the group, they're again in the same row. I had also written down the proof. And same for columns. And so, for example, this has already this consequence. If you have a bunch of numbers that are a connected component of both graphs, then in here, any element of the group acts like a tensor product. So there will be two permutations, sigma and V, so that it acts separately on X and Y. So anyway, so I just wanted to give you a feel. If you have an isolated vertex, then the connected component in the other one is only isolated vertices, etc. And this is an idea of how these results were obtained, and I will stop here.